sample size estimations. I emphasize the word estimation. Believe it or not, well over half of the consults that one gets as a statistical consultant is for estimating sample size. And that's appropriate. Some sample size calculations are complicated, but most are not. And so our goal is to deal with those common, relatively straightforward sample size calculations, which are the kinds that are mostly appropriate for the types of studies you will do and read. We do have some objectives for this session. It's a little bit different from our other sessions. We're going to do both didactic and hands-on at the same time. By the end of this session, I would like you to be able to do a sample size calculation for common experimental designs, and we're going to talk about some of those common experimental designs using either lookup tables or online calculators or statistical software in particular, and not just R. I'll show you some other examples too. If you already know how to do a sample size calculation, I'm still hoping this will be a useful session because you'll get some hands-on experience doing those calculations, again, for common designs. But probably most importantly, and if I were feeling better, I would stand up on the table and rant on this point, I really want you to understand that it is unethical to endanger or inconvenience patients and to consume medical resources that are costly and scarce, by which I mean mostly your time, for a study that is inadequately powered, that can't answer its primary question. There's no point in doing that study. And people don't realize that, and it breaks my heart when I see somebody present the results at the end of their 4 years of study, and I do my sample size calculation while they're talking, and I say, you've come to a conclusion, and you would have needed 4 times that many patients to actually come to that conclusion. So your 4 years of effort was a waste. That's what I'm trying to avoid, because that, I think, makes for bad science and also a bad experience, scholarly project experience for you. So those are my goals. Sometimes you need to consult a statistician or do some additional reading. Chow's book is very good. It's in the library, called Sample Size Calculations in Clinical Research, for more complicated designs. But for the most part, as we will see today, most studies can be powered based on 4 simple scenarios. You're comparing means between groups. Chris, what's the test we use to compare means? I have no chocolates today to motivate.
I feel like that heat test?
Yes. So that's what we're going to use to power our studies when we're comparing means. Or our studies are going to be designed to compare proportions or counts. So Amarjot, what test do we use to compare counts?
Is it the
Yes, it is. And in fact, when we're comparing 2 groups, which is mostly what we do with sample size calculations, there's an even simpler version of the chi-square test called the binomial distribution, which is the coin flip distribution, and we're going to learn about that. But yes, you're right. Sometimes, not all studies, and this is really important, people misunderstand that. They think, oh, I have to be comparing one group with another or one group with 2 other groups to do statistics, and that is not true. Sometimes we're doing what's called a single sample study, and a single sample study would be something like, I want to report the mean birth weight of babies in Winnipeg. And I'm not comparing them to anything, I just want to know what the mean birth weight is. And in this case, people will stand up and say, I didn't have to do a sample size calculation because I wasn't comparing anything. That is wrong. As we saw in the WIP last week, even Bav was doing a single sample study. She was trying to characterize these kids who got ceftriaxone in the emergency room, and her goal was to estimate the population proportion who successfully responded to short course therapy. So she wanted to estimate 4 days or whatever the duration was going to be with some predetermined precision. So she wants to say, I want to get a number of days of treatment or a mean birth weight plus or minus 100 grams or plus or minus 500 grams. And I want to get it with a certain level of confidence. So even when we're doing a single sample study, there is still a power or sample size calculation that we need to ask ourselves. How many patients do I require to estimate what I'm trying to estimate, the population parameter, mean birth weight, duration of treatment, whatever it is, with sufficient precision to make this study useful? And it may be plus or minus 10%, it may be plus or minus 30%. It depends on your study. So, but it is perfectly legitimate to do a single sample study. The other situation where we do a single sample study, where we're not comparing 2 groups, or three groups, is when we're studying the relationship between variables. We might be studying the relationship between height and weight, and in that case, we often look at the correlation between two continuous variables, and we'll learn how you do a sample size calculation for two continuous for a correlation between two continuous variables. This is a very good book, Hulley and Cummings, Designing Clinical Research, by which I mean it's also short, as you can see. I would recommend it for anyone who wants more detail. It's in the library, and the department has a copy kicking around somewhere. I don't think you have that, Celia, do you? John must still have it. The primer, the research guide from the Royal College, chapter 25, is a chapter on sample size calculations. It's fairly basic. I am going to distribute to you, and these are the last I have, so I'd ask you to pass them around, but these are the tables from Hulley and Cummings. And I would suggest you hang on to those tables, because otherwise you have to go to the library and get the book. And as we're going to see today, they're a very useful way to do sample size calculations very quickly, just by using lookup tables. So there are 5 tables there, I think. Table 13A is when you're comparing two means for a continuous numeric variable, and we're using a t-test. 13B is when we're comparing proportions in two groups, like the proportions with hypertension or the proportions who are overweight or obese. And we're going to use, we're going to either use a binomial distribution, which is a distribution for coin toss, a yes/no variable, or we're going to use the Z approximation to the binomial distribution, because you will remember when I was flipping coins and demonstrating to you the central limit theorem that if my sample size is large enough, I can approximate it as a normal distribution. So virtually every sample size calculation we do is based on a normal distribution somehow. Table 13C is when you have two continuous numeric variables like height and weight, and you're studying the correlation between them. And then the last two tables are for descriptive studies. These are single sample studies, and one is when you're trying to decide how many subjects you need to estimate some population parameter with a certain degree of precision and confidence for a continuous numeric variable or a binary yes/no variable. So we're going to use those tables, and that's what they cover. When I first started preparing this talk, I was trying to do something along the lines of sample size calculations for dummies, and probably none of you read those books, but I like them, and they always start with a list of 10s, so I wanted to create my own list of 10. And this is my list of 10, in which I wanted to outline the essential information that you need to collect before you sit down and do your sample size calculation. I'm going to run through this list. If you're not familiar with some of these items or you're not sure what they mean, don't worry, because we're going to cover them in detail. So the first thing you need to do is identify if you're, well actually I should, number 3 I'm going to say first. The first thing you need to do is to decide whether your study is descriptive or experimental. By experimental I mean you're actually comparing groups. So you may be comparing two groups for mean blood pressure or mean weight or some such. A descriptive study is what I just called a single sample study. So in this case, it's still required that you do a sample size calculation, but the aim is different. So the first thing we'll do is decide what type of sample size calculation are we doing. Are we doing a multi-sample study or a single sample study? As we've talked about several times, you need to identify your outcome variable, sometimes called the disease variable, and your exposure variable, also known as the predictor variable. And that's particularly true in an experimental study where you're comparing groups. So there is no study ever that looks at a single outcome. You usually have multiple objectives in your study, and that's perfectly fine. But you do need to decide what your primary outcome is, because typically we power our studies based on the primary outcome. And we may be underpowered for secondary outcomes, but they're secondary outcomes, and we don't worry so much about that. So your study power will usually be determined by what you have called your primary outcome. For an experimental study where we're comparing groups, you will need to specify a null hypothesis, which we call H0, and an alternate hypothesis, which we call H1, and we'll define those more clearly in a moment. You will also need to select how big an error you're prepared to live with. And we've talked briefly about type 1 and type 2 error rates, also known as alphas and betas, respectively, and we're going to define those more clearly today. You will need to decide whether you're doing a two-tail test or a one-tail test. And the other way to think of that is this a directional test? I'm asking myself, how many subjects do I need to say that the mean blood pressure in one group is higher than the mean blood pressure in the other group? That would be a one-tail test. A two-tail test would be, how many subjects do I need to answer the question, is the mean blood pressure different in these two groups, without specifying a direction? It's very tempting to say, well, I only need half as many patients if I do a one-sided test. But it's unusual to do a one-sided test. The FDA doesn't like them, and we're going to talk about circumstances where it would be appropriate to do a one-sided test. Probably the most difficult question people ask is, or that people struggle with when they're doing their sample size calculation, is you have to decide what the effect size is. How big a difference do you want to see? Let's say I'm doing a blood pressure treatment, and I'm giving a medication and a control or another medication. How big a difference is clinically significant? Is 1 millimeter mercury difference in blood pressure going to justify calling the trial a success? Is a 10 millimeter difference going to justify calling it a success? That's the effect size. What is the minimum detectable difference you want your study to be able to see? And in order to define an effect size, you have to have some idea what the expected values are going to be. You have to have some idea in advance of what you're going to get for a mean blood pressure. And I want to emphasize to you here, and this isn't to frighten you, it's to empower you, that this is a clinical decision. People come to me all the time and say, well, what effect size should I use? And I have to say, sorry, you're the clinician. You have to decide what your effect size is. So that's a very important decision that you have to make when you're calculating your sample size. If we're dealing with a continuous numeric outcome, mean blood pressure, mean weight, mean height, you have to have some estimate of its variability, which means you have to know its standard deviation, and we'll see why in a few minutes. And that can be hard to find. Often we can go to the literature. Sometimes there are no reported standard deviations in the literature. You still need that number, which means you can go to an experienced clinician and get some idea of the variability that they've seen in their clinical practice, and that's okay. Or you can do a pilot study where you take 10 patients and estimate the standard deviation, but you do need that number when you're dealing with continuous numeric outcomes. As we'll see, you don't need that number if you're dealing with proportions. If we're dealing with proportions like a binary outcome, yes, no, heads, tails, live, die, you need to identify whether you're doing a prospective cohort study or a retrospective case control study. And we talked about odds ratios the other day and alternatives to odds ratios, and we're going to talk about that a little bit more today. And then lastly, you have to identify a probability model for testing your null hypothesis. And that means you're going to say, I'm using a t-distribution for a t-test to compare means, as Chris just pointed out, or as Amarjot pointed out, a chi-squared distribution or a binomial distribution to look at differences in counts or proportions. So that's my list of 10. Now let's talk about what those mean. The variable type, as I said on the first day here, automatically determines the appropriate statistical analysis. So please remember your different types of variables. Nominal categorical variables, you will recall, are arbitrary categories where they have names but there's no intrinsic ordering to them, like hair color, treatment A versus treatment B, disease versus non-disease. When we're doing sample size calculations, we try to make our categories binary or dichotomous, so it's yes, no, 0, 1, disease, non-disease. There are also ordinal categorical variables where there are categories, but those categories now have an order to them. So it's a semi-quantitative scale, low, medium, and high blood pressure, the 6 grades of congestive heart failure, 1, 2, 3+ on a dipstick. Histopathology is often the pathologist gives their impression of, say, the degree of inflammation is 1+, 2+, 3+. Or Likert scores from a survey where you, at integer values, 0, 1, 2, all the way up to 10. These are all examples of categorical variables. Continuous numeric variables are basically, are also called interval variables, and they're basically variables that can take on any numeric value, technically from minus infinity to infinity, though the negative values may not be realistic for weight or blood pressure. So when we're doing sample size calculation, they're actually astonishingly easy for most experimental designs. For a continuous numeric variable, Chris has already told us, we're comparing means, so we're going to use a normal distribution or a t-distribution, typically a t-distribution. If we're comparing a binary categorical variable, we're interested in proportions or counts, and we're going to use a binomial distribution. And really, that's it. So I remind you briefly that the normal distribution we use for modeling continuous numeric variables is completely defined by two parameters. It's mean mu and its standard deviation sigma. If we standardize that to calculate a z-score, we now have a normally distributed variable with a mean of 0 and a standard deviation of 1. That's called the standard normal distribution. And the reason this is important is because the standard normal distribution has a probability density function that relates the probability of any value that it can take on to its mean and standard deviation. And obviously you don't need to know that formula, but you do need to know the consequences. And we've talked about these before. The mean plus or minus 1 standard deviation covers 2/3 of the distribution. The mean plus or minus 1.96 standard deviations covers 95% of the distribution, and so forth. And more importantly, we can calculate the probability of, let's say we're interested in z of -2 or less. We can calculate the probability between any 2 points on this distribution by doing the integral. So if we were interested in what proportion of children with normally distributed height will be between z equals -3 and z equals -2, we just calculate the area under this curve, which is an integral, between -3 and -2, and you look up the value of that integral in the back of the book. But that's what you're doing, is you're doing an integral to calculate an area. If you want to say how often is a normally distributed variable going to be above this point, we calculate the area from 3 to infinity. And again, all of those are in the back of the book. Even though the z distribution is our standard go-to tool, we usually don't know mu and sigma, and we have to use sample estimates for the mean and the standard deviation, in which case we're no longer dealing with a z distribution, we're now dealing with a t distribution. And you'll remember that t distributions have different degrees of freedom depending on how many parameters have to be estimated. Like here we lose a degree of freedom because we have to estimate the mean. And so instead of n degrees of freedom, we would have n minus 1. And the difference, I know I've already covered this, but just remember that the t distribution sees unlikely events out in the tails happen more often. And so that's why you don't want to underestimate unlikely events, and that's why we use a t distribution. The central limit theorem is important, and again, we've gone over it in detail, but I'm just going to remind you, it has to do, it comes into play whenever you're measuring some quantity x in random samples of size n. And basically what it tells you is that regardless of the distribution of x, the mean value in that sample will be normally distributed. So if I calculated 100 different means from 100 different groups of size n, the resulting distribution would be normal. And so I can use, because they're normally distributed, I can use all the magical properties of the normal distribution or the t distribution to make statistical inferences, to calculate p-values, to calculate standard errors, to calculate confidence intervals. And I can do all of that even if x is not normally distributed. And I showed you an example where the binomial distribution is highly non-normal. This is a 2-parameter distribution. Here you see there's a formula for it that says the probability of any number of heads in n coin flips is determined by the head probability or the success probability p. So it's 2 parameters, n and p. Like the normal distribution, it's completely defined by 2 parameters. It can only give you 2 values, 0 and 1, yet if you do this experiment 1,000 times, you can see that the mean is very normally distributed. So even though Amarjot said we're going to use a chi-square distribution or a binomial distribution, which is the 2-sample equivalent, the truth is that we often use the normal approximation, even when we're dealing with proportions. And so these tables, for instance, are approximate. And they'll say we're using the Z approximation to the binomial distribution. So we talked about probability models. We always formulate our null hypothesis, that straw man that we're trying to disprove, in terms of probability distribution. So when we're comparing means using a Z or T distribution, we calculate sample means and sample standard deviations and sample standard errors. And you'll remember that the means are normally distributed and they have their own standard distribution. And that standard distribution is related to the standard distribution of whatever we're measuring. And so the standard deviation of mean blood pressure is called the standard error of the mean, or SEM, and it's just the standard deviation of blood pressure divided by the square root of the sample size. And so there's a very intimate relationship when we're using the Z or T distribution between the standard deviation and the standard error. Now, when we're dealing with proportions, we again get a sample mean, which is just the number of heads divided by the number of coin flips. And we also get a standard deviation. But what's different here, and this is a really profound difference, is that the standard deviation, we don't have to calculate it because it comes from knowing the success probability and the sample size n. And so that's what I mentioned earlier, that whenever we're doing a sample size calculation, it's actually easier if it's based on a proportion because we don't have to find in the literature what the standard deviation is. It follows automatically from the binomial distribution. Okay, is that clear to people that you only need to know it some of the times? Okay. So predictor variables, also known as, you need to know your variables. The predictors are also known as exposure variables or treatment indicators. They may be binary, yes, no variables. They can refer to risk factors. Do they smoke? Do they not smoke? To treatments. This patient has renal artery stenosis. Did they get an angioplasty, yes or no? They may be continuous. Outcome variables, also known as the result or the Y variable or the disease variable, and they can also be binary or continuous. As I mentioned, you need to identify your primary outcome, even if your study has multiple outcomes. We will still choose a primary outcome for our sample size calculation, and again, it can be binary, which we're going to deal with as a proportion. Do these children have renal artery stenosis, yes or no? Did they respond to treatment with angioplasty, yes or no? Or it can be continuous. What's their mean blood pressure? What's the Doppler flow velocity in the renal artery in the stenotic segment? What's their plasma renin activity? What's their serum potassium? These are continuous measures. So you need to clearly identify what you're dealing with, and you need to clearly identify what type of study you're doing. And again, I mentioned this very briefly. Most studies end up being experimental. We're comparing groups, and we're asking ourselves, how large a sample size do we need to compare these two groups with sufficiently small error rates? And we'll talk about type 1 and type 2 errors in a minute. Or is this a single sample study where our goal is to estimate the mean population parameters like mean birth weight or mean blood pressure for a population? And now we still have a sample size calculation. And I'm not kidding you when I give this talk and residents put up their hands and say, I don't have to do a sample size calculation because I'm not comparing anything. Yes, you do. You have to say, how large is your sample size going to need to be to make your estimate with a desirable level of confidence? So as the example in the WIP, Bav did the sample size calculation, and she said that she was trying to estimate the proportion of children who were successfully treated with 4 days of ceftriaxone. So she was trying to estimate a number like 90% with a certain degree of confidence, with a certain degree of precision, plus or minus 10%, say, and a certain degree of confidence, like 95% confidence, which means the estimate would be correct 19 times out of 20. You hear that on news polls all the time. And that's her sample size question, is how the sample size will be different if she's content estimating the population proportion as 90 plus or minus 30. She's going to need a different sample size than she would need if she has to estimate it with a precision of 90 plus or minus 1. So that's where the sample size calculation comes into a descriptive or single sample study. There are a couple of common errors that I'll warn you about Your actual study may have more than one outcome, may be very complicated, but we would still base our sample size calculation usually on a simple study design and on a two-group comparison of our primary outcome, whether it's a mean or a proportion. Please remember that the sample size is not definitive. It is a rough estimate of the sample size you'll require. In many ways, it's an informed guess, and you're trying to assess the feasibility of your study design. It makes a difference if you do your sample size and it says you have to review 1,600 charts to do your study versus you have to review 100 charts to review your study. You're trying to get a rough idea. In my list of 10, we talked about null and alternate hypotheses that describe the differences we expect to see between groups. They are mutually exclusive. Our null hypothesis is simply the hypothesis of no association between our groups or between our predictor, which is our group indicator, and our outcome, which could be mean blood pressure or birth weight or what have you. And what we want to do is we want to test, there's always going to be a difference if you measure it sufficiently closely. The question is whether or not the observed difference or the strength of the association you see between those two variables is due strictly to chance, and that's where the p-value comes in. And so the null hypothesis will require us to specify a particular probability distribution because we want to calculate a probability of a certain event. We also have an alternate hypothesis, which is just the opposite. There is an association between the predictor and outcome. You cannot prove an alternate hypothesis. All you can say is there's enough evidence to reject your null hypothesis. And I mentioned the other day, just think of it as the presumption of innocence in a jury trial. It's unprovable. Null and alternate hypotheses should be kept simple. Let's say you're studying hypertension and renal artery stenosis, and your subjects are getting angioplasty. The null hypothesis could be something as simple as there is no difference in plasma renin activity following angioplasty. The alternate hypothesis could be as simple as saying there is a difference. So this is a two-sided alternate hypothesis. If I have enough prior knowledge, I might say my null hypothesis, I might want to impose a directional hypothesis saying plasma renin activity goes down after angioplasty. But usually we'll use a two-sided hypothesis unless it's very clear from prior knowledge that a one-sided test is appropriate. As I mentioned, in 1990, the FDA actually issued guidelines in saying that we don't care if you think a one-sided hypothesis is appropriate. We prefer you use a two-sided alternate hypothesis, and what they were basically saying is that if you're going to use a one-sided hypothesis, the onus is on you to persuade the reviewers, editors, funding agencies, that with compelling evidence that only one direction makes sense. And sometimes only one direction makes sense, and it is appropriate, and we'll see some examples. Type 1 and type 2 error rates, when we refer to them, what I'm saying, the type 1 error rate determines the significance level or the p-value that you're going to associate with your study. The type 2 error rate determines the power. So let's go over this again because I find people get confused. A type 1 error is a false positive. You reject the null hypothesis of no difference when in fact it's true. There is no difference. So if I set p equals 0.05, I'm accepting a 5% chance of falsely rejecting the null hypothesis by chance. And we call that the alpha. So alpha in this case would equal 0.05. And it's the risk I'm prepared to live with. And there's nothing magic about 0.05. I was just reading Scientific American on the weekend, and they were trumpeting some observation on cosmic ray particles that destroys the foundation of the standard model in physics. And they said they were confident in this result to 5.8 sigmas, which means a p-value of 10 to the minus 17. Now, that's interesting because the particle physics literature actually requires 6 sigma. P equals 0.05, as you realize, is a 2 sigma level of confidence in a result. Particle physicists insist on 6 sigma, so 10 to the minus 18. So in fact, they were reporting a trend at 5.8 sigmas as if it was a definitive, groundbreaking result, and that sort of annoyed me because you shouldn't adjust your results arbitrarily. Really, that's all. By their own standards, they could only be reporting a trend. We, on the other hand, would be absolutely thrilled if we had a p-value of minus 10 to the minus 17. And so the point I'm trying to make is that every discipline has its own standard. You should also appreciate that there is huge variation, even in the medical literature. In JAMA in April, there was a piece written by 73 expert statisticians making the case for a whole bunch of different p-values depending on the nature of the study. And it was accompanied by an editorial by Johnny Ioannidis, who said, this is too complicated, we should just take p equals 0.005 as our cutoff. And so I think you're going to see people move away from 0.05 toward 0.005 as their type 1 error rate. So 0.005 means you're willing to live with a 0.5% chance of a false positive. Type 2 error rate is just the opposite. It's a false negative. I accept the null hypothesis. I say there is no difference, when in fact there is a difference. H1 is true. And just to confuse you, we refer to the beta, which is the type 2 error rate, just like the alpha is the type 1 error rate. And we usually say we're willing to live with a 10 or 20% beta. So we're willing to live with a 10 or 20% false negative rate. But to confuse you, we don't often refer to beta, we refer to the power, which is 1 minus beta. And that's all the power is. So an 80 or 90% power means there's an 80 or 90% chance of seeing a real difference, that's actually there, which means a 10 or 20% chance of missing it. In most sample size calculations, people will use 80 or 90, depending on how much money they're trying to get. There's nothing wrong with using an 80% power. Sometimes, depending on the importance of the findings, their clinical significance, not their statistical significance, people will even want 95% power. They really don't want to miss a difference. So I made this little table just to show you what type 1 and type 2 error mean, but we've gone through the definitions. Is that clear to everyone that type 1 error is a false positive where we reject the null hypothesis inappropriately, and type 2 is a false negative where we accept the null hypothesis inappropriately? One-tailed or two-tailed hypothesis, I'm almost done this didactic part, bear with me. Remember, a normal distribution has two tails, so there are two ways that we could reject the null hypothesis and commit a type 1 error, because the treatment group could be down in this tail or up in this tail. So in a two-tailed test, our alternate hypothesis is simply that the mean in the two groups is different, and so it could be up here or it could be down here. In a one-tailed test, our hypothesis may be directional. So the mean blood pressure, the mean plasma renin activity in kids after angioplasty is lower than in kids who don't have angioplasty or in themselves before angioplasty. So here we have a directional hypothesis. It does reduce your sample size, but as I mentioned, it really does require compelling clinical or biological evidence that only one direction is important or only one direction is possible. So I'd ask you to bear that in mind. Choosing an effect size, I mentioned, confuses people. It is simply the size of the association between your predictor and outcome. It's the difference that you hope to see, and it obviously depends on the type 1 and type 2 error rates that you're prepared to live with, because actually, that's incorrect. I should have written smaller samples. I should have written smaller differences actually it is correct. Smaller sample sizes are limited in their power to discriminate or discern differences. And so if you have a small sample size, you are able to see only larger effects. And that'll become clear in a moment. Where do you get your effect size from? Well, you have to review the literature. You may have to do a chart review. You may discuss with a more experienced colleague. You may have to do a pilot study, review some charts in your own clinic to get an idea. In choosing the minimum detectable effect size, I emphasize again, you're making a clinical, not a statistical decision, and only the clinician can judge the difference between a clinical and a biologically important effect and a statistically significant effect. Sometimes you don't know what the effect size is, and that's okay. You can systematically study the relationship, and I'll show you an example of this, between sample size and effect size, and you can, from that, say, put my finger right here and say, I arbitrarily choose this point based on budgetary and time constraints. And again, the onus is on you to persuade the reviewer that that's reasonable. I mentioned earlier that when there's more variability, there is a greater likelihood that the two groups will overlap. And so the minimum detectable effect size depends very much on the variability. And when we're comparing means, it depends on the standard error. So here's plasma renin activities in two groups. And you can see when the standard error is 2.5, those two means have a fair overlap region where you will not be able to tell them apart. When the standard error is 1, it should be pretty clear which population the mean is drawn from, because they're quite distinct. So this is how variability affects power. For a numeric outcome, which we're modeling as a normally distributed variate, you do need a standard deviation or a standard error. And that means, again, you have to consult the prior literature or a more experienced colleague or do a chart review or a pilot study. For a proportion, you'll recall that I told you that the standard deviation is related to the proportion. So you don't need a separate estimate of the standard deviation. This is for a binomial distribution. You can calculate for any value of outcome, of success probability, you can calculate the binomial distribution, standard distribution, and standard error. So your sample size formula don't require a separate estimate, and that can make them easier. So sometimes if you say, look, I've looked, I can't find a standard deviation, well, base your sample size calculation on a proportion, like the number above the median or the number above the 90th percentile or some such, and then you don't need a standard deviation. Someone asked me a question about this the other day. I can't remember who it was. It might have been you, Will, about odds ratios. Someone asked. Anyway, so I said I'd come back to it. You have to decide whether your study is a prospective cohort study or a retrospective case control study. So in a cohort study, we're prospectively following groups, usually two groups, and our samples, our two samples, are the groups with and without exposure for some disease. So let's say our disease is lung cancer, and our exposure is smoking and non-smoking. So we have two groups, smoking and non-smoking. We're following them prospectively. In a case control study, we identify cases with diseases, and then we find controls without lung cancer, so those are our two groups, plus or minus disease. And now we're comparing their exposures. So it's important to understand, in this case, we know the denominator. In this case, we don't. And where it gets confusing is that both of these types of studies are summarized by a 2x2 contingency table. And in a prospective study, we're interested with the risk, which is just the number of kids who get a disease, or let's say the number of smokers who get a disease, divided by the number at risk. So our samples are exposure, smokers versus non-smokers, and our proportions, or our risks, are the number who get lung cancer divided by the total number of smokers. In the other group, it's the number who get lung cancer divided by the total number of non-smokers. We calculate the risk for each of these, and then we take the ratio, which is a risk ratio, or a relative risk, or an RR, which is just proportion 2 over proportion 1. And it's given by this formula here. So because you have to know the denominator, the relative risk is only meaningful in a prospective study. In a retrospective study, our two groups are those with and without disease. And we're going to compare how many of the disease patients have exposure versus how many of the disease-free patients have an exposure. And to do this, we calculate the odds in each group. And so you will remember that the odds is not the proportion that gets disease, it's the number with an exposure divided by the number without an exposure. So in this case, if we say P2 is the probability of an exposure, then the odds of exposure in this group, the group with lung cancer, so the odds of smoking in the group with lung cancer is just A, the number who smoked, versus divided by C, which is the number that didn't smoke. And in the other group, it's B over D, and that's the odds. So the odds is not the same as a risk, because we don't need to know the denominator to calculate an odds. But the same way we calculate an odds ratio, and we get this algebraic expression here. And if you go back to the previous slide and you consider the case that when the disease is rare, you will see these two expressions actually become the same. The odds ratio is a very good estimate of the relative risk when the disease is rare. But even if the disease is not rare, the odds ratio still measures the strength of the association between the exposure and the disease. So odds ratios have the advantage is that they're meaningful in either a retrospective or a prospective study. So if you're asking yourself, I think someone asked this the other day about a relative risk, yes, in a prospective study, by all means, use the relative risk, but you can use an odds ratio for both. So just to summarize, and then we'll take, I have 2 more slides. You've seen this slide before. The information you need to collect. The most difficult, I think, are the effect size and your expected outcomes, and also some estimate of the variability for a continuous numeric variable, particularly the standard deviation for that measurement. There are common errors that people make. Don't forget to include, to budget for dropouts. The number of dropouts will be very study specific. But the sample size calculation depends on the number who complete the study. So you have to allow for dropout rates. The dropout rates will depend on how onerous your investigation is. Is it just a survey they do in the clinic, or does it involve a liver biopsy? It'll depend on how aggressively you or your research assistant pursue patients to make them come back for follow-up. Where do you get your dropout rate from? Again, from the literature, more experienced colleagues, or a generous estimate. Don't confuse the standard deviation and the standard error. They're very easy to calculate one from the other, but you have to be using the right one. And I'll make one last point, and then we're going to start doing some examples. One last point is, we've been talking here about equivalence trials. The null hypothesis implies that the two groups are the same. Drug companies in the last decade or so have gotten into what they call superiority trials or non-inferiority trials. They're a little bit more complicated. They're trying to show that a drug, a treatment is better than the existing treatment, or that to show that the treatment is no worse. And the calculations are still based on the same principles, the binomial distribution, the normal distribution, the areas under the curve, but they're a little bit more complicated to do. There are packages for doing them, and this is a good reference if you're looking for more information, but I'm not really going to talk about those today, because I think if you're doing a superiority trial or a non-inferiority trial, that's where you want to get a statistician involved. So that's the boring bits, I promise you. We're going to now do some real-world examples. So the first one, we're going to consider 2 different asthma treatments. And some of you will not believe this, but when we were pediatric residents, we didn't have inhalers. Those came later. So this drug of therapy for treating asthma exacerbations was intravenous theophylline, and aminophylline in particular. And you may not know this, but aminophylline is a great drug, but it has an extremely narrow therapeutic window. So at a level of 12, they're subtherapeutic. At a level of 20, they're bang on therapeutic, and at 25, they're vomiting blood and seizing. So a very big job for the pediatric resident. This is what I spent many nights on call doing, was starting IVs and drawing aminophylline level or theophylline levels. And so it was a really big thing when they came out with inhaled salbutamol or metoprolol and those other beta-2 agents. And so let us imagine you're in those days and you're asking yourself, you want to compare the FEV1, so the forced expiratory volume, which is a measurement of flow in 1 second, or the volume expired in 1 second, with 2 different asthma treatments. So, Susan, tell me what my predictor and outcome variables are here. And also, what kind of variables are they?
So your predictor is the treatment.
Yeah.
And then the outcome would be your FEV1.
Okay. And what kinds of variables are there?
So your predictor the treatment is a categorical, and then your FEV1 is continuous.
So how am I going to compare the continuous number in those two categories?
You're comparing two continuous variables, so you can do what's it called? T-test.
Yes, absolutely. That's exactly. See, this is fairly simple. So I'm going to do my FEV1, which is the 1 second forced volume. I do it 1 hour post treatment, and I'll standardize it, and I'm going to compare the mean. So, Andrea, what's my null hypothesis and my alternate hypothesis here?
So your null hypothesis would be that there's no difference between the two treatments, and the alternate would be that there is.
Yeah, and I think that you're quite right. In this case, I've given you no information to suggest one is better than the other, and we really, to be conservative, we should go with a two-sided hypothesis. So let me give you some information from the literature. Whoops, got the wrong way. So if you look in the literature, you will find that metoprolol, that the effect size, the difference, is about 200 mils in an asthmatic patient. So the mean FEV1 is about 2 liters, but the difference between, sorry, I take that back. In the literature, what you will find, because I looked at this, is that the mean FEV1 is about 2 liters, but then you have to ask your respirology colleague how big a difference in FEV1 is clinically significant. And that's where the 0.2 comes from, because the respirologist told me that, well, 200 mils would be a significant difference. Less than that, they're not going to regard that as helpful. So that's where we got our effect size. Now, when we're using lookup tables, as we're going to use here, we often, just to make the tables easier to use, talk about a standardized effect size, which is just the effect size divided by the standard deviation. So here, too, I need the effect size, which is a clinical decision. I need a standard deviation, and I calculate the ratio as 0.2. So let me hide that. What's my, Kaylee, what's my type 1 error and my type 2 error that I'm going to live with here?
So for a type 1, we usually use like the alpha 0.05 or p 2.5.
Yeah.
And then your beta or your power, I guess it depends on what you want to do, either 80 or 90.
Yeah, and I usually do both, but 80 is perfectly reasonable. And appreciate, though, that you may miss a difference of 0.2 20% of the time. It's good to to go with the higher number if it's feasible, because inevitably you end up getting, something happens. You end up getting less power than you expected. So 90 is good, but let's do this one with 80. Those tables I circulated, which are from this Designing Clinical Research book, make it very easy to do simple calculations. So I'm first going to show you how to do it that way. So our effect size, which is expressed as a standardized effect size, is 0.2. So that's 0.2 liters over the standard deviation of 1. And I said that we have decided together we're going to do a two-tailed test with an alpha 0.05 and a power of 80%, which is a beta of 0.2. And I follow this column down until I meet the effect size, and I see that I need 393 in each group. Now that's a lot of subjects. I'd ask you to bear that number in mind, because we're going to talk later about ways that we could reduce that number. Because remember, we need 2 groups here, so or we're going to use, if we're using 2 groups, we need 393 in each group. These tables are very easy to use. This one says t-test for comparing means. That's what we're doing. There are also online calculators. Russell Length at University of Iowa has a lovely calculator. There are many you'll find, but I would recommend his if you're looking for something. He has a nice note that says, you would not perform brain surgery without being qualified. You should take the same approach to sample size calculations. His is a Java applet. You dial in the standard deviations, the alpha, the power, and you say you want a sample size, and you get 393. So exactly the same. In R, which you're all familiar with now, there's a power t-test function. And it can be used for many different things, but this is the way you use it. Here I've said n equals null, so I want it to tell me the sample size. The effect size, or delta, is 0.2. The standard deviation is 1. My alpha, or type 1 error, is 0.05. My power is 80%, and I'm doing a two-sided test in 2 samples. And I really like it when I get the same result from several different methods, but here it summarizes that information and telling me that I need 393 in each group. Now, power calculations, that term power calculations refers to more than just sample size. For instance, you might tell me that you only have 300 patients and you just can't do more. So in that case, the question may be, what's the smallest effect size that you can see? And in this case, I've stipulated n equals 300 and I've left blank the effect size. Everything else is the same. And now I'm seeing that instead of 200 mils, the smallest effect size I can see is basically 230 mils. And that might be perfectly fine. So you could say I've got alpha equals 0.05, beta equals 0.2. I can see a difference of 230 mils. As long as you appreciate that, that there may be a smaller difference that you're not powered to see. I mentioned earlier that it is sometimes helpful to, this is called a power plot, to make a plot of sample size versus effect size. So you can see here, the change could be 0.2 or all the way up to 0.5, and then my sample size, as my criterion becomes less strict, my sample size becomes smaller. And I really like putting power plots into grant applications because it makes it look like I thought about the problem. And it also allows the reviewer, more importantly, to say, well, I disagree with your choice. I think a difference of 0.3 is enough, or I want 90% power. And so it allows them to reproduce the calculation easily. You should always give your reviewer enough information. It's not enough to say, I did a sample size calculation and it came out of this. You have to tell them what your assumptions were. So you have to give him or her the sufficient information to reproduce your calculations. And let me tell you, if I get a grant application and it doesn't have a sample size calculation in it, I toss it out. I will not review it because I have no way of knowing whether or not it's feasible. So this is not just a game we're playing, this is really important. The other thing that you can do with that power t-test function is you can say, what's the power? So someone could say, no, I need to be powered to see a 0.2 difference. I only have 300 patients. What's the power of that? So everything else is the same, except I've now left power blank, and I have a 68% power, 69% power. Karen, what's that telling me?
So 32% of the time you will falsely, or so you won't pick up that
Yeah,
difference.
that's right. Yeah.
That
And so,
you could define.
yeah, so despite the fact that I've written the answer on the slide, do you think that's adequately powered? No, I think most of us would agree that's an underpowered study. So you can see this function and those tables are handy. You don't have to use R. SAS has a proc power function. You have to give it exactly the same information. Reassuringly, it gives us the same answer. Stata has a samp sci function. Again, you give it the same information, it gives you the same answer. So many studies that you will propose, that's it. That's your sample size calculation based on comparing 2 means. Let's do another comparison of means, but this time in a case control study. So let us say that we have stroke patients and we match them with controls who didn't have a stroke or were in hospital for some other reason. And we're interested in their serum cholesterols. And so we measure serum cholesterols in both our cases and controls. I've already asked you, right, Rachel? Or no? Yeah. Oh, okay, sorry. So tell me, what are your predictor and outcome variables here?
So your predictor is the serum cholesterol, and the outcome is whether or not they have a stroke.
Yeah, that's right. Now, remember here, this is case control, so you're absolutely correct, but
So
I've
like the
identified...
stroke patients that you've already identified
Yes,
versus
exactly.
the control
But
side.
the exposure and predictor you've got, you're correct. So what type of comparison, Rachel, am I doing here between, what am I comparing and what type of comparison?
So I guess your predictor is a continuous variable, and your outcome is a categorical binary.
Yeah. So what am I comparing?
So your outcome, you're, I guess, comparing proportions.
I could, but I have a continuous numeric variable.
Okay.
I probably want to compare their means.
So we're doing the t-test.
Yeah, to compare means, exactly. So I'm going to use exactly the same table. Alexandra, what is my null hypothesis and what's my alternate hypothesis?
And all that there's no difference between the case and the control. And then the alternate one is that there is no.
Yeah, exactly. And so I'm going to use exactly the same table. I'll give you some information now in the literature. Controls, these are elderly patients, I guess. So this age group have a mean serum cholesterol of 200 milligrams per deciliter and a standard deviation of 20, which means an effect size. That's my mean and standard deviation. I talk to the neurologist and the cardiologist, and I say, well, how big a difference do you think it's important, would be clinically important? And they tell me 10 milligrams per deciliter, which means I have a standardized effect size of 0.5. So, let's hiding that for a second. Tell me, Mary, what my error rates are going to be and whether I'm going to be doing a one-sided or two-sided alternate hypothesis.
Your error, so your 52 alpha would be 0.05, and then it would be a 2
There's absolutely nothing wrong with that. One could argue that in this case, there's a lot of conflicting literature out there that sometimes there's no difference. Sometimes controls have lower cholesterols. Would that influence your choice of power and whether or not you did a one-sided or two-sided test?
I want my power to be like on the higher side.
Yeah, exactly. So you might favor in this case, yeah. And given that the studies have either showed no difference or higher in stroke patients, would you feel comfortable arguing that this could be a one-sided test? Yeah. So that's the point I wanted to make, is that it just because I say we try to be conservative, sometimes you can argue that, no, I've got a lot of literature out there. None of it says stroke patients have lower cholesterols. They either have no difference or they have higher cholesterol, so I'm going to power my study based on that. So I'm trying to emphasize to you that these are not concrete rules. You get to decide as long as you justify them. And so we'll do that. We'll do, in this case, we'll do a two-tailed test, but we can do it both ways. We use the same table again because we're comparing means by t-test. And Will, I haven't yellowed in the answers here. Do you want to give it a try?
Okay, so we said 0.05 for the alpha.
Yeah. Yeah. That's
And
right.
then 0.1 for the beta.
Yeah.
So that would give you 17, 13.
So what's my standardized effect size?
I can't remember.
It was 0.5. It was 0.5.
0.5.
Yeah. So I need to know that.
Oh,
Sorry. Over here. So two-tailed alpha 0.05.
Yeah.
Power of 90%, and effect size of
So
84. Now, one of the reasons why I like these tables, besides the fact that they're blindingly easy to use, is that you can see very easily what changing your assumptions does. You can say, well, what if I wanted a one-sided test? What if I wanted more power or less power? It's very easy to adjust it here. For instance, if you wanted 95% power, like let's say because the literature is conflicting, you want to resolve this question, and so you don't want to miss a negative result. You might want 95% power. It only takes you 20 more patients in each group, so that might be worth it. So again, the table allows you to do what we call sensitivity testing your assumptions by varying. But you can do the same thing using your software. In this case, our effect size is 10 with a standard deviation of 20, and that's where the standardized effect size of 0.5 came from. Alpha is 0.05, power is 0.9. It's a two-sided test, and we wanted to estimate the sample size, and we get 85 patients in each group. So we get the same result, and you get the same result if you use Russell-Lentz calculator. So let us move on to another example. We've been talking about means, either prospectively or retrospectively. Let us move on to proportions. So let's say that we have an ambitious dermatology resident who wants to study the association between skin cancer and smoking in a cohort that they're going to follow prospectively for 5 years. So, Amarjot, what are my predictor or exposure and outcome variables here, and what kind of
The
variables?
predictor exposure would be the smoking, and then the outcome is going